Today we will be presenting on reducing the encapsulation bottleneck associated with mRNA vaccine production.
Our project's main goal was to analyze the microfluidic physics that occurs in the T-junction apparatus. The T-junction is where two flowing channels containing mRNA and lipids mix and create LNPs or lipid nanoparticles, which are used in mRNA vaccines for COVID-19. We used COMSOL and simulated the micromixing process that occurs in the T-junction. In addition, we aim to analyze parameters that could potentially affect encapsulation characteristics, such as shear stress and its relationship with LNP size. This approach was completed in a laminar flow regime, and increasing our understanding of parameters and their relationships with encapsulation characteristics, such as rate and size, will lead to a more efficient production of LNPs. As a result, vaccine throughput will skyrocket and lead to a decrease in vaccine price, which ultimately leads to more countries being able to afford vaccines for their populations. mRNA is a single-strand RNA molecule. Its backbone consists of a ribose sugar and phosphate molecules. In cells, the DNA is transcribed into instructions that make proteins. These instructions, which are the mRNA, travel from the nucleus to the outer part of cells. And once the mRNA reaches the ribosomes, they are translated and proteins are made. The type of protein that is made depends on the nucleobase arrangement and the mRNA strand. And for mRNA, they are adenine, cytosine, guanine, and uracil.
An overview of the current mRNA vaccine production can be seen below. The current process for production can be divided into 5 parts. These include the transcription reaction, which produces the mRNA, followed by mRNA purification, after which mixing occurs, which formulates the mRNA into LNPs. This is followed by the purification of LNPs, and then packaging into vials for distribution. The step with which we are most concerned is the third step, the mixing or formulation of mRNA into lipid nanoparticles. This step includes a cleaned mRNA buffer solution being mixed with a diluted lipid ethanol solution to form LNPs. Step 3, as previously mentioned, is the main bottleneck for the production of mRNA vaccines due to the inherently low throughput associated with the 1.5 millimeter diameter tubes. Based on the literature review, it is still unclear what flow regime is responsible for the encapsulation of mRNA into LNPs. However, most researchers gathered the dominant flow regime for the process is closer to that of laminar flow. As such, our COMSOL model was created using laminar flow physics. The figure shown above shows the velocity profiles over the total tube diameter of 1.5 millimeters at different points in time. Due to the rapid flow rate of 0.2 millimeters per second, the encapsulation process happens very quickly and was measured over a period of 10 milliseconds. As can be seen, the velocity profile resembles that of plug flow, as the gradient of the velocity profile increases quickly from the wall to the center of the tube. This is indicative of a very high amount of shear stress, which can be seen nearest to the walls. Based on the review of the scientific literature, the shear stress undergone by the molecules was found to have a significant effect on LNP formulation, thus leading to the encapsulation of mRNA. Based on this finding, further analysis of shear stress was done.
As mentioned prior, the shear stress that molecules undergo affects LNP formation. We desire higher shear stress values for the creation of LNPs. The reason behind this is that it enables the lipids to rapidly form and close into a sphere around mRNA strands in the channel. Referencing the figure shown, one can determine that the shear stress is at its peak value near the tube wall. Analysis of the results indicates that the higher shear stress values exist while moving towards the side walls of the T-junction and were most prominent at an input velocity of 0.1 meters per second. Understanding the mechanism behind the bottleneck helps increase the throughput of the process and thus cut back on cost. The resulting savings can be passed on to customers in countries that are limited in financial resources to adopt a widespread vaccine program. Modeled after an 8 billion dose program over a 6-month period, the current price per dose of a Pfizer vaccine is 84 cents. A 20% decrease in the time taken to encapsulate mRNA would bring this cost down to 79 cents. Since the goal of most vaccines is total population inoculation, This reduction by a few cents makes a significant difference when scaled up to billions of doses.
For the next step, we suggest looking into further configurations and simulating their fluid behavior through COMSOL. This will in turn be used to conduct data analysis, which will lead to the development of the model. We'd like to thank our faculty advisor, Dr. Cho, for helping us and guiding us throughout this process. This would not have been possible without him. Thank you again, Dr. Cho, and thank you for everyone for watching.